Comparing two proportions, part 2. At the end of the last video, we quickly went over step 3 and 4 as I was running out of time on the video, but I'd like to clarify. In order to find our confidence interval, we take our difference from our two proportions, which in this case was negative 2.2, plus or minus some margin of error, which is our z-value, 1.64, times the standard deviation. And our standard deviation is given by this formula right here. Well, as far as the work you need to show, you do need to show the z-score, and it'd be nice if you could show the standard deviation, but honestly, I would really be okay with you showing this much, the point estimate, or the difference of negative 2.24, plus or minus the margin of error, and then just state the z-score, since the calculator will tell you that. Or will tell you that using inverse norm. So let's start about z-score first. Again, if we want a 90% confidence interval, we do inverse norm for 0.95, which would give us a z-score of 1.64. So that would go right here in our formula. The next thing we need is the standard deviation. Now you could absolutely figure it out by putting in the p-hat value for the Plavix people times the q-hat value for the Plavix people divided by the number of people in the Plavix section, plus the p-hat value for the standard treatment times the q-hat value for the standard treatment divided by the number of people that had the standard treatment, and take the square root of that. But I'm not asking you to do that. Instead, state the z-score because IB wants it, or excuse me, AP wants it, which is 1.64, and then go ahead and find the margin of error. Now, the margin of error is just the difference from the top value or the bottom value of the confidence interval and the point estimate, or negative 2.2. So you could do that by saying negative 0.013 minus 0.022, and converting that, okay, which would give you a margin of error of 0.09. An easier way to do it would to go ahead and find the average of the two, or the middle, take the lower bound of your confidence interval minus the upper bound of your confidence interval and divide that by 2. And again, you would get the margin of error. So what I really suggest is you just do it in the calculator. And I'm going to show you another one where I've done it in the calculator. And the amount of work I'm then requiring is for you to list the z-value and show me that it's the point estimate plus or minus the margin of error. And then you can clearly state your conclusion, which is that I am 90% confident that the true difference of the, let me see what it is again, excuse me. The true difference of further complications between patients that have taken Plavix versus patients with the standard treatment falls between negative 0.0309 to negative 0.013. And therefore, here's the key thing. Because both of these are negative, and if it was negative, it meant Plavix is better, I can say Plavix appears better. Now, it doesn't necessarily mean it's that much better, because look how close to 0 our bottom value is. But overall, it appears better. Here's the last example. In a 1997 article in the USA Today, they reported that in a survey of 150 males aged 20 to 24, 72 live with their parents, and in a similar survey of 150 females aged 20 to 24, 51 live with their parents. And the question is, does this give convincing evidence that 20 to 24-year-old males are more likely to live with their parents than females of the same age? So the first thing I did was I found the proportion of males in this, and there were 150 males, 72 out of the 150, or 48%, still lived with their parents. And then I went ahead and looked at the females. 51 out of 150, only 34% lived with their parents. So right now it looks like more males still live at home. And we're going to subtract them to truly figure that out. And what we have here is it says, at first glance, it appears that the proportion of males aged 20 to 24 that live with their parents, and I'm going to make that, I'm going to go ahead and define the variable p hat of m, and it appears it's greater than the proportion of women ages to 20 to 24 that live with their parents. And again, I'm going to go ahead and define that. That's p hat of, and I did f in this case. Excuse me. Define those. Since p hat of m minus p hat of f is equal to 0.14, which is greater than 0. However, it is possible that the true proportions are the same, and we got a difference this large due to sampling variability. Again, it's sampling this time because we took a sample of people already living at home. We didn't randomly assign them to live at home. To decide, we'll conduct a 2-sample z-test for the true proportion of males minus the true proportion of females at an alpha level of 0.05. Now I need to state my hypotheses. My hypotheses, or my null, is that the true proportion of males minus the true proportion of females is equal to 0. They're actually the same. And my alternate hypothesis is that the true proportion of males, notice that I have the p hats here and not here because we're talking about what we saw in our observation or our sample versus what we truly think is happening. Anyway, that the difference is greater than 0. And let's just double check. Yep, they are more likely to live with their parents, so it's going to be one-sided greater than 0. Now we need to check our conditions. Well, randomness was not specified, so right now we would proceed with caution, but we also need to check NP, NQ. So the number of people that were men times the p hat of the men, that would be 0.4, that would be 150 times 0.48, which is equal to 72, and that is greater than 10. I'm going to go ahead and do the same thing with the number of males. Having an issue with my pen. I'm going to go ahead and pause this and fill it in because my pen is being weird. Okay, anyway, I did the number of males times the proportion of males that live at home with their parents, and that was greater than 10. I also did the number of males times the failure proportion, or those males that did not live at home with their parents, and that gives us 78, which is greater than 10. I did the same thing for females, and all of those are greater than 10, and I should write in the greater than 10. I was just having an issue with my pen. So our normality condition is okay, but our randomness is not, so again we will proceed with caution. Step 4. We're going to go ahead and do a 2 proportion z-test, put everything in, and we will get a z-value of 2.47 and a proportion of 0.0068, and which means we were trying to find the probability of the difference being greater than 0.14, which is the same thing as testing the probability of a z-score being greater than 2.47, and we get a difference of 0.0068. And so now we can conclude, since the p-value is less than the alpha level, we can reject the null hypothesis and assume that more men live at home than women. Now, you might have noticed we went from hypothesis testing to confidence intervals back to a hypothesis test example, and that was because I wanted to show you one of each in class. I'm also going to run this data in a confidence interval to see if we get the same thing. This time we want a 2 proportion z interval. We had 72 men out of 150 that live at home, 51 men out of 150 that live at home. I'm going to do a 95% confidence interval, and I'm going to calculate and in this case I get a confidence interval between 0.02 and 0.25. That whole interval is above 0, so again it matches our hypothesis test that says we can reject the null and assume more men live at home. because our test for the percentage of men that live at home, or the difference of the percentage that men live at home, is greater than 0, showing more men live at home. So there you go.